here or here, we're going to have a value function that's v of the successor state. Okay, and we're going to get some immediate reward along the way. So this diagram is just kind of showing us that we can think of this as a one-step look-ahead tree, where you start in this state, you look ahead one step, you integrate over the probability of each of these function here. Okay, so it's a one-step look ahead with like this averaging, where we kind of go ahead one step, we average all the possible outcomes together, and that gives us the value function at this step. And that's actually kind of the way that we're going to proceed when we actually start to build algorithms. They're going to do something like this look ahead process, which is why it's useful to have these backup diagrams in mind. Okay, so if we think about the value function now, let's just pick out one state. So if we pick out this state here, so this is the class 3 state. And so I'm just going to tell you that this is going back, I think this is a discount factor of 1 now, so it's undiscounted. And what we're looking at is what happens if we're in this state with no discounting. So I claimed that this was the value function of this MDP, but how can we verify that? Well, we can use the Bellman equation to verify that. We can say, okay, well, if this value function is 4.3, it should really be equal to doing like a one-step look ahead, averaging over all the things which might happen next, and then ending up back here again. Okay, so let's see if that's really true. Well, from here, there are two things which could happen. So we could either basically get, so we're going to get -2 immediate reward no matter what happens. Okay, that's this -2 here. And then with 0.6 probability, you're going to move through to the next class and end up somewhere with a value of 10. But there's also 0.4 probability that you'll go to the pub and you'll end up in this state which had a value of 0.8. Okay, so if we sum those things together, we get -2 plus 0.6 times 10 plus 0.4 times 0.8, which to numerical precision is 4.3. Okay, and so that sort of validated the fact that this really is the value of this MDP.
I'm not very clear. What is this capital R represents? Is it a reward for doing a step?
This is
no matter where.
Okay. So I think I need to be clear about the rewards. I think a few people are. So let me try and explain that more clearly. What this diagram represents is that you're in some state. When you exit that state, regardless of what you do, you will get the reward indicated by this R. Okay? So upon exiting that state, regardless of where you end up, you will get this -2. So we could have duplicated this and written R -2 here, R -2 here, and it could have been on these arcs. And actually, when you define Markov reward decision processes, which we'll see later, and for Markov reward processes, you can make it dependent on the particular arc that you take. You can make it dependent on the action. You can make it dependent on the successor state. All of these things are possible. This is the simplest formulation. The rewards just depend on the state that you're in, and that state determines how much immediate reward you'll get. And then you have to look at where you ended up to see how much immediate reward you'll get on the next step. So you start here, you exit it, you get -2. You get to here, you exit this state, you get -2. You exit this state, you get -2. You exit this state, you get R equals 0. Okay. Sorry, you get +10. You exit this state repeatedly, you get 0, 0, 0, 0. Yeah, last question, then I'll move on.
I guess that's the reason why one needs to exit the past state to get the reward of +10 to go to sleep.
Yes.
That's why.
Yes, thank you. Okay, let's move on. Okay, so this Bellman equation, so far we've seen how to kind of spell this out literally state by state, but there's a much more concise formulation which is using matrices and vectors. So if we just spend a moment to understand that, what we can do is basically use this matrix formulation of the transition matrix, which we've already seen. But now what we're going to do is we're going to introduce a vector representation of the value function, which is the obvious thing. It's basically we form a column vector where each element of the column vector contains the value function of a specific state for all states from 1 to n. Okay? And so now we can write out our Bellman equation very concisely. It's just that the value function that you start with, this column vector here, is equal to, and we're going to do the same thing with the reward function as well. We're going to write out the reward function with one element per state. This tells us how much reward you'll get from exiting state 1, all the way down to how much reward you'll get from exiting state n, so forth. Okay, so this is your immediate reward, and then this is how much, this is where you'll transition to, and this is how much value you started with before. Okay, so it's basically telling us that in one sweep we can just look at this thing. We can say the value of this state is equal to the immediate reward plus the transition matrix. So these are all the places we might transition to, and then this is the value of where we end up. Okay, this is the value of, after I've taken a step, I might end up in this state, I might end up in this state, I might end up in this state. And each row of this thing is going to be dot producted with these values. So there's some probability if I'm in this state that I end up in each of these successor states, and then we take the dot product of that with all of the values of where we end up, and that's going to give us this first entry here. So it gives us, literally, it's a way of writing out the entire Bellman equation in one very concise form. Okay, yeah, question?
Transition matrix, should that be N1?
Yes, that should be Pn1, thank you, in the bottom left. Okay, so the Bellman equation is a linear equation. As a result, it can be solved directly. It's one of the nice things about linear equations. This is not going to be true once we move to the more complex case with Markov decision processes. It's a nice property of just evaluating the rewards, but once we want to maximize rewards, it gets harder. But at this stage, at least, we can solve this directly. Assuming that our matrix is small enough to invert, what we can do is just write out our linear equation now. All we're going to do is collect together the v terms here. So we've got, if you like, identity times v here, and gamma p times v here. So we collect those together on this side, I minus gamma p, v equals r, and then we just invert this matrix. Okay? And this is the solution to the MDP. The computational complexity of inverting this matrix is n cubed for n states. So this is not typically a practical solution method for large Markov processes. So what we'll start to look at in subsequent lectures is efficient ways to solve these problems. In particular, this is just going to be a building block. All of the things we've seen so far are just building blocks towards what we really care about, which is making decisions. And so this is just going to be a building block. We need to be able to efficiently figure out what's the value of being in this state. We can't always do this. But it is nice to know that in small Markov reward processes we can just invert this thing, and it gives us some intuition into what's going on. So later we'll talk about, next lecture in fact, next class is dynamic programming. That's a very well-known class of methods for basically doing this more efficiently. Then we'll talk about Monte Carlo evaluation and temporal difference learning. That's like, the next couple of lectures are basically doing exactly that. Right. So that was sort of the elementary building blocks leading up to this point, which is the MDP. This is the thing which we actually use in reinforcement learning. And so I guess I should pause. Any questions so far? I guess we've been doing them as we go, so. Right. So the MDP, we're basically going to add in one more piece of complexity now, which is actions. So far there's been nothing for us to do. I just told you get plonked down in your student Markov reward process, and you just randomly sample these transitions and get spat out at the other end. You didn't get any, you didn't have any agency. You weren't able to take actions and make decisions. So let's now change that. Let's introduce decisions. So what we're going to do now is basically take our Markov reward process, which was a state space, transition matrix, reward function, and discount factor. We're going to add in one more component, which is the action space. So A is now a finite set of actions. In the extensions to the class, you'll see how this can be made continuous or infinite. But for now, we'll consider the simplest case. This is a discrete set of actions, finite size. And so now what we're going to do is say the transition probability matrix now depends on which action we take. So where you end up is now going to depend on the action that you take. If you move to the left, the probability that you end up in all these different states is going to be different to if you choose to move to the right. The wind might blow you different ways in each case, but you have some agency over where you're going to end up. So the way we think of this is that there's just one, in the discrete case, there's like one separate matrix of transition probabilities for each action that you might take. And now we've got this reward function. The reward function, again, may depend on the action. May also not depend on the action. But in general, this thing can depend on the action. Apart from that, everything is the same. The machinery is the same. We've just introduced actions in the simplest possible way. So what we're going to do is actually redo our student Markov process now, but as an MDP, where there's decisions that you can take. So the decisions are now these red labels on the arcs. And so the point now is that you actually have some agency here. And so from this state, you can choose to either study. That's a choice now. So there's no probabilities attached to this. You can choose to study. If you study, you end up in this state. If you choose to go on Facebook, you end up in this state. When you're on Facebook, you can choose to do it again, or you can choose to quit. You can choose to go to sleep here or to study again. You can choose to study again, or you can choose to go to the pub. If you choose to go to the pub, that's the only place now that there's any randomness. If you choose to go to the pub, who knows what might happen? Maybe you'll drink 1 or 2 beers, not quite sure. So now there's some probability that you'll end up going back to class 1, going back to class 2, or even going back to class 3. Okay? So there's a lot more control that you can exert now over your path through this MDP. This is the reality for an agent. And the goal is, the game we're playing now, is to try and find the best path through your decision-making process that maximizes the sum of rewards that you get. That's the game that you play in an MDP. Okay. So to do that, the first thing we need to talk about is formalizing what it means to make decisions and to take decisions. And to do that, we define something called the policy. So the policy is basically, we can talk about stochastic policies today, and these policies are distributions over actions given states. So in other words, if you're in some state S, this distribution basically gives you the mapping. It says, like, if I'm in this state, map from that state to some probability of going left and some probability of going right. So this is the thing that tells me if I'm in class 1, I am going to choose to go to class 2 with probability 0.9 and to go onto Facebook with probability 0.1. This is something under the agent's control. It's something we decide, and it's just a stochastic transition matrix. And it's useful to make it stochastic because that allows us to do things like exploration. So we'll make use of that later in the course. So once you have a policy, it completely defines how that agent will behave. And in an MDP, the policies depend just on the current state. That was the Markov property. It doesn't depend on the history. And as a result, we consider what we call stationary policies. We don't consider so all of the policies the same no matter what time step we're in the MDP. We just have the same policy at each time step. And the only thing that this depends on is the state that we're in, not the time step at which it happened. And that's sufficient to behave optimally because by definition we have the Markov property and this state S fully characterizes everything that will happen next. Yeah, question?
How comes there is no rewards variable here at all? I mean, surely if you want to maximize rewards, you should take it as a simple concept, no?
The question was, why are there no rewards in this equation? And that's because the state S fully characterizes your future rewards. So in a Markov reward process or Markov decision process, the Markov property means that S fully characterizes the evolution from this state onwards in the process. And so what you're looking for is the policy which, given the state you're in, will you want to pick actions that will get you the most future reward. And so all you need to look at is what state am I in and what action should I take next. And we're trying to pick those actions in the way, given that state, that will get us the most future reward. So the rewards are in the future. We don't care about how many rewards we've got in the past. Those rewards are gone now. They've been consumed. All we care about is how much reward we can get from now into the future. So we don't actually care, when we try to maximize this thing, we don't care if we've already achieved 1 million reward or minus 1 million reward. That's irrelevant. What we want to do is maximize the reward from now onwards. That's the way we're going to behave optimally.
Our definition of state, information-wise, includes all the information about the expected future rewards, right?
Yes. Yes. Exactly. Okay. So one important thing to note about the connection between Markov decision processes and Markov reward processes is that we can always recover an MRP or a Markov process from our decision process. So just to understand that, we can think about basically the sample of states that we draw. Like if we have some policy that helps us pick actions, we're just going to draw this sequence of states. And the sequence of states that we draw when we follow our particular process is actually a Markov chain. It's a Markov process itself. No matter what policy we choose, that policy defines some Markov chain that actually defines our dynamics, the way that we're going to move through and evolve through this system. And if we look at the sequence of states and rewards that we receive as we pass through, like once we fix the policy, if you fix the policy and look just at the sequence of states and rewards that you see as you go through this MDP, that sequence is a Markov reward process. And the way to understand that is that we're going to define basically transition dynamics and a reward function which just average over our policy. So we're just going to average over all the things which happen under our policy. We're going to average over, so we're going to define the transition dynamics to be the average of the transition dynamics for all of the things that we might do. So if we're going to go left with probability 0.5 and right with probability 0.5, I'm just going to take 0.5 times the dynamics, or the probability of going to all the states from here, plus 0.5 times the probability of all the states that I'm going to end up in over here, sum those together, and those average dynamics define some Markov reward process. So we can always flatten our MDP, given our current policy, back into a Markov chain. This is just a useful point. It's not like central, so you can come back to this and think about it offline if you like. Okay, what is central is the concept of the value function. So we already had the value function for a Markov reward process, but there was no agency there was no decisions. Now we've got this policy. There's some way that we can choose to behave in our Markov process. You know, I might be following this path straight through the student Markov chain where I collect all the rewards by going through all the classes, or I might choose to spend a lot of time on Facebook. These are going to give different rewards. There's not one expectation anymore. There are different expectations depending on how I behave. And so we subscript our value function by the policy that we're interested in evaluating. So v pi of s now tells us how good is it to be in state S if I'm following policy pi. So if I'm following the policy that just goes straight through the classes, how much reward will I get? Or if I'm following the policy where I stay on Facebook for as long as possible, how much reward will I get from each day onwards? And so this basically is defined, we've just got this expectation here now. This e pi basically means the expectation when we sample all actions according to this policy pi. That's sort of hidden in that e pi notation. We're also going to define a second type of value function called the action value function. So far we've got the state value function. This v we call the state value function. That tells us how good is it to be in a particular state S. We're also going to define the action value function, which tells us how good is it to take a particular action from a particular state. And this is the thing which we intuitively care about when we want to decide which action should I take. Should I go left or should I go right? Well, I should choose the one that's going to give me more reward. And the way I evaluate these things is by looking at the action values. In other words, we're basically going to look at, so q pi, so for a given policy, for a given way to behave, we want to know if I'm in this state S and I take this action A, what's the expected return, the total reward that I'll get after I've taken that action, how much reward will I get from that point onwards? Okay, that's the key quantity that we're going to use to help us optimize our MDP and pick the best actions. So let's make this concrete again. So this is the state value function for the student MDP, undiscounted, so the discount factor is 1. And this is just for uniform random behavior. So we're fixing the policy to say we're always, when we've got a choice, we're always going to randomly pick 50-50 between those choices. Okay? And so this is the value function that we end up with. We see that we end up thinking it's not very good to start in this state here because there's a high probability of ending up in the Facebook state because we're choosing things 50-50. Now what we can define is another Bellman equation. So the Bellman equation, we saw this in the Markov reward process. Now we're going to define a Bellman equation for these value functions in the MDP case. So again, we can use the same idea, that the value function can be decomposed into an immediate reward plus the discounted value at the next state. So again, there's this idea that wherever you are, you take one step and you get your immediate reward for that step, and then you look at the value of where you end up, and the sum of those things together tells you how good it was to be in your original state. That's still true in an MDP. Now what we're saying is that you start in this state, and we know that we're following policy pi, but the value of being in this state is still the immediate reward that you get, plus the value of your successor state if you know that you're going to follow policy pi from there onwards. So we just look at what happened for one state for one step of following a policy, and then we ask how much more reward will I get following that policy. When we sum those things together, that gives us the Bellman equation. We can do the same thing with the action value function, with these Q values. And this basically tells us now, if I'm in one state and I take an action from there, then I'll get some immediate reward for that action, for that specific action. And then I'll look at where I end up, and I can ask, well, what's the action value of the state that I end up in under the action that I would pick from that point onwards? Okay. So let's look at these kind of pictorially and try and understand them with these sort of look-ahead search diagrams. So the way to understand this is, first of all, to understand how V and Q relate to each other. So if you're in a state value function here, really what it's saying is that we're going to average over, basically we're going to average over the actions that we might take. So there's some probability that we'll take this action here. These black dots represent actions and these open circles represent states now. So we're in some state here. We might take this action here. We might take this action here. The probabilities of these things are defined by a policy. So this is like the probability I'll go left, the probability I'll go right. And for each of those actions we might take, there's a Q value. There's an action value telling us how good it is to take that action from that state. And so what we're doing is we're doing like a one-step look ahead, saying the state value, how good it is to be in this state, we just look ahead one step, look at the action values, average them together, and that tells us the value of being in that state at the top there. Now let's do the converse, understand the opposite step. So what happens if we start off taking some action? So now the root of this tree is a state, and we're considering a specific action that we take from that state. So that's this black circle here. So this is like saying, you know, I'm in this particular state here, and I'm asking the question, how good is it to go right from that state? Okay, and how good it is, we now have to average over the dynamics of our MVP. The environment might blow me over here. The environment might blow me over here. So after I've gone right, I might get blown to all these different situations. And we want to ask, for each of these situations I might get blown to, how good is it? What's the value of being in that situation under my current following my policy after that point? We average over all these things using the probabilities of our transition dynamics. We average them together, and that gives us the action value function at the root here. Okay? So V is telling us how good is it to be in a particular state. Q is telling us how good is it to take a particular action from a given state. State value function, action value function. We can put these together now. So this is basically just stitching together the two figures from the last two slides. And now what we'll see is we get like a recursion that helps us understand V in terms of itself. And this is how we end up solving Markov decision processes. So at the root of the tree now, we've got the value function for a particular state. It tells us how good is it to be in this state. And the way we're going to understand that is by doing a two-step look ahead. So we can look ahead, we can consider all the actions we might take next. Go left, go right. We can consider all the things that the environment might do to us. It might blow me over, it might keep me standing up. It might blow me over, it might keep me standing up. There are all the things the environment might do. And then for each of those things the environment might do, there's some successor state that we'll end up in. We want to know, well, how good is it to be in that state and carry on with my usual policy? How much reward will I get if I carry on from that point? Now, if we average these things all together, we're basically averaging in two ways. Now we're averaging over our policy. We're weighting each of these arcs by the probability that our policy will select left or right. We're averaging each of these arcs by the transition probabilities that will end up getting blown in one direction or another. We average it all together, and that gives us the value of being in the root of this diagram here. It tells us how good is it to be in a particular state. So this is the Bellman equation. You can do exactly the same thing for action values. There's a recursive relationship. You can look at this offline. I don't want to sort of belabor the point. But it's just stitching the diagram together the other way around, and we end up with exactly the same idea, that starting from a particular state in action, we can now look ahead 2 steps, consider where the wind might blow us first now, and then consider, from the state the wind might blow us to, which action might I take next? I might choose to go left, or I might choose to go right. And now we average over this thing again. We look at the value of that particular action, the Q value, average these things all together, and it tells us something about the Q value of this start action here. So the Q value relates to the Q values at the next step, in this slide and in the previous slide, the state values here relate to the state values at the next step. So you get these two recursive relationships explaining how the value function relates to itself at the next step. But in all of these cases, if you just look beneath the math, it's a very simple idea which says the value function at the current time step is equal to the immediate reward plus the value function of where you end up. That's all these things are saying, just with different ways of putting together the maths. Okay, so let's do that for one example in our student MDP, and then we'll move on a little bit. So here's our student MDP again. We're going to consider just one state, this red state here, so the class 3 state. And again, I'm just going to verify, we're not kind of using this Bellman equation to compute these value functions. We're going to use it to verify that this indeed does have the value of 7.4. Okay? So how can we verify it? Well, we can unroll, we can do our look ahead. And what we're going to do is we're going to do our look ahead for the state value function here. So we're saying the state value function of 7.4 is equal to all the things which we might do from there. So what are the things we might do from there? Well, we might study. Remember, we're doing things 50-50 with for now, with 50% chance we choose to study and 50% chance we go to the pub. So under that policy, where we do everything 50-50, so yeah, this whole diagram is showing us the value function for the policy where we choose all of our decisions 50-50. And under that policy, we start in this state. There's a 0.5 chance we'll take this arc and get plus 10 reward. That's this part here. There's also a 0.5 chance we'll end up taking this arc, end up in the pub, and the pub might take us with 0.2 probability over here, 0.4 probability over here, 0.4 probability over here. And in each of those cases, we'll end up in a different state with a different value. So there's a 0.2 chance we'll end up in this value state here with value minus 1.3. There's a 0.4 chance we'll end up in this state with a value of 2.7. And a 0.4 chance we'll end up in this state here with a value of 7.4 again and end up where we started. So you can see this is quite cyclic, this thing. And so that's this equation here. We just sum those things together. So we're summing together this look ahead of what might happen after one step of taking actions and one step of where we end up. And when you add this together to one decimal place, you get 7.4. So we've sort of verified that these numbers are self-consistent for this one state. You can verify them for all of the other states, and you would discover that this Bellman equation does indeed hold, and therefore these numbers do represent the value function for this MDP. So that basically tells us now we really know how good is it to be in each one of these states. You really will get 7.4 units of reward in expectation if you just behave according to this policy. Okay, is that clear? Right. So, that's all very well, but it doesn't tell us the best way to behave. And what we really care about in an MDP is figuring out the best way to behave. Okay, just briefly, before we do that, so I briefly introduced earlier, and I said it wasn't essential, but this idea that you could flatten any MDP back into a Markov reward process by defining these averaged state transition dynamics and averaged reward function. And of course, once we've averaged those things, that gives us a Markov reward process. We know how to solve those things already. So at least one way to solve that, another way to have solved for these numbers would have been to form these matrices, form the matrix of our transition probabilities for all of our actions, average them together to get our p pi, average together our immediate rewards to get our r pi, solve for this equation here, and that would have spat out our actual value function. So that's one way to arrive at the solutions, and we'll look at more efficient ways to do it going into the future. But you should at least understand the idea that the Bellman equation gives us a description of the system that we can solve. Once we solve for this thing, it tells us exactly what the value function is. So one linear equation, we solve it, you've got the value function, you're done. Okay. Right. Now, for the last half an hour, I want to talk about the essential problem we really care about, which is finding the best behavior in the MDP. But I'll just pause for a moment, sorry, I know there's a lot of material, so any questions at this point? People
the
tracking?
slides online are slightly different, just minor changes to these. Are you going to put the newest ones online?
I'll put the newest ones online immediately afterwards, yeah. So it's mostly notation change. I changed the notation to match the new edition of Sutton and Barter.
Can you just explain again what happened to the state pub, which seemed to have turned into some other... It used to be a state, right?
Yeah, so when we moved from the Markov reward process to the Markov decision process, we changed the definition of the problem. So pub used to be a state, now it's a decision that we're making. We're taking a decision now. So we're making these decisions of whether to go to a pub or whether to study. So it's actually a different problem that we're studying now.
So pub is an action now.
Here, pub is an action, yeah.
But it ends up at something which isn't a state, whereas study ends up in something which is a state. So what?
No, everything ends up in a state. So if you take the pub action, you end up at this black dot represents like a chance mode.
You mean you can't stay there?
You can't stay there, no. The action takes you to here, and the environment immediately transitions you to here, or to here with these probabilities.
Right.
So you can think of this as basically telling you the dynamics. So if you take this pub action, you're basically going to be teleported to here, or here. You'll get a +1 reward along the way, and the probability of ending up here, or here is given by these numbers.
But
That's what it means.
Okay. Why did you do that? I don't understand. Why did you now have this separate sort of this sort of transient state?
Because I wanted to illustrate an example where you have some agency, where you have some control over what happens in the environment.
Right.
And now it's a choice whether to go to the pub or not. And the randomness is now what happens after you go to the pub.
So all the other states could be considered to be the same as that, but with just a probability of 1 of going to their
Exactly.
next
Everything,
state.
you can implicitly imagine there's one of these black dots in every one of these other arcs. So if you go to Facebook, there's a black dot here that says the action is taking you to that black dot, but that black dot is always taking you here with probability 1.
Okay.
And actually now, they say that action also have rewards.
Mhm.
Earlier on, we were saying only that the states has rewards, and now that's actions.
Yeah, if we go back to the this was all in the definition of MDP. So if we go back to the definition of MDP, the red highlights here indicate what changed from the Markov reward process. And one of the things which changed was that the reward function was now indexed by both state and action. So the reward does depend on the action you take. That's the definition of an MDP. Okay, so what you do might affect the immediate reward you get as well as the state you end up in. So sometimes there's a cost to the action you take. That's the simplest case. Like imagine a trading agent, you buy £1,000 of goods from someone. That immediately costs you £1,000 compared to the action of do nothing, which costs you 0. So there's a cost associated with the specific actions, and they take you to different states. So that's really the commonest case. So you should intuitively expect that rewards have different effect depending on the particular action you take.
So it's a form of non-determinism then, really, this sort of possibly taking an action but ending up probabilistically in one of a number of different states.
An MDP is stochastic. The stochastic transitions depend on the action that you take. So you get to take an action, the environment gets to roll the dice and tell you where you end up. So it's a combination of your actions and the dice which get rolled by the environment which determine what happens next. Okay, good. Where were we? Okay, so now let's talk about how to find the best possible solution to the MDP. So what we really want, we don't really care about how much reward we'll get following this crazy 50-50 policy in the student Markov chain. What we care about is finding the best path through the system. In general, you want to find the optimal way to solve your problem. And so let's define what that really means now. And so we're going to start with value functions. We're basically going to say this V star, the optimal state value function, V star, is the maximum value function over all policies. Okay? So what we're saying is there's all kinds of different policies we could follow in our Markov chain, and what we care about is the best of those. We care about understanding what's the maximum possible amount of reward that you can extract from this system. There's all these different ways you can traverse this system. Each of your different policies is going to lead to a different evolution. Stochastic evolution, we care about which of those is going to lead to the most reward in expectation. That's V star tells you not what the best policy was, but what's the maximum possible reward you can extract from the system. Similarly, the optimal action value function, Q star, tells you the maximum amount of reward you can extract starting in state S and taking action A. So given that you actually commit to a particular action, what's the most possible